The refresher on network layer leads us to IP networking, and it's about IP addressing and routing. And when you have some networks of different technologies, you have IP subnets and you route from IP subnet to another IP subnet. And from source IP address to destination IP address, you can route through these networks. It's store and forward, and it's stateless. Any router doesn't remember a previous packet, and it just selects the forwarding interface by looking into the routing table, and then it forwards the packet. So the routing tables are essential for routing. And the IP protocol describes how IP addresses are built, and you have public IP addresses, and the network mask is important to define the network, and you have private IP addresses. And for some networks there's a second level of addressing, which is the autonomous system, but we will not cover autonomous systems in our lecture here. Then there's gateway functions of IP addressing, which means you can interconnect from one transmission technology to the other transmission technology by using a router. Looking into IP version 4, you have 20 bytes of header, 5 rows of 4 bytes, and we have some fields here. Most important fields are the source IP address, 4 bytes, and the destination IP address, 4 bytes. Time to live is not a time, but a hop count, how many hops can be passed. Any hop will decrement the number here, and when you reach 0, the packet is dropped. And an error message, ICMP TTL exceeded, is sent back to the source. In the version field, you will have a 4 for version 4 and a 6 for version 6. IP header length counts the number of rows, and here we have 5 rows, so 5 is the normal value in IP version 4. Typical header length is 20 bytes, and this leads to important correlation with the maximum transfer unit on layer 2. If you have an MTU of 1500 bytes, you can only have 1480 bytes encapsulated in IP version 4 packet to prevent fragmentation. If we add TCP, the most used transport protocol, it has a maximum segment size, and this will only have 1460 bytes because TCP additionally adds 20 bytes of header. Here's a list of the header fields. I'll rush through it. And here is a capture of an Ethernet frame which encapsulates an IP packet. We have the frame layer, and we see 74 bytes on wire. The FCS is missing. Then we have Ethernet with the source and destination MAC address and the other values of Ethernet frame. Then we have the IP packet, and here it's version 4, 20 bytes header. Type of service field is 0, so it's best effort. And important, the encapsulated protocol is 1, which is ICMP. In this case it was an echo request, which is a ping, and you see there are also echo replies. And the source address is 192.168.1.109, and destination address is 192.168.1.1. We must understand that IP addresses relate to the network mask, because any IP address has a network portion and a host portion. The network portion defines in which network devices are connected. Host portion defines the individual host in that network. And the mask describes how long is the network portion, how long is the host portion. The network portion in the mask has only ones, and the host portion has only zeros. If you want to calculate the network you're connected to, you can use the IP address of the device and end the mask with that IP address, and you will get the network address as is described here. If you use the IP address and or the inverted mask, you will get the broadcast address. In our example, 192.168.10.10 is in the network 192.168.10.0, and the broadcast address is 192.168.10.255. We have some special IP version 4 addresses, for example, private IP version 4 addresses. These are not routed in the internet, and we need network address translation to get connectivity to the internet. Private IP addresses are 10.0.0.0/8. It's a class A network with 10s at the beginning. We have 172.16.0.0/12. It's the range of 172.16 to 172.31. All addresses in these areas are also private IP addresses. And we have 192.168.0.0/16. And this is the range from 192.168.0.0 to 192.168.255.255. And these are also private IP addresses. And finally, one special range is link local 169.254.0.0/16. Then we have some local host addresses inside of your operating system, and used for that is the class A network of 127. Another important aspect is that if you have classful networks, you can subnet these networks. Class C network is /24. 3 bytes are ones, 1 byte is 0. And in this example, we have a given class C network 192.168.10/24. And we cut it into 2 subnets by borrowing 1 bit from the network mask and setting this bit from 0 to 1. So the mask gets 1 additional 1 and 1 0 is deducted. And we come to a network mask of /25. And when you apply the calculation of networks to this, then you will get 2 subnets now. One subnet is 192.168.10/25. Network mask is 255.255.255.128. First usable IP address is 1, last usable IP address is 126, and broadcast is 127. The second subnet starts at 128/25, same subnet mask with /25 once. And first usable address is 129, last usable address is 254, and broadcast for this subnet is 255. From one network we get 2 networks equal sized. And we borrowed 1 bit from the class C network mask. If you would borrow 2 bits, we can have 4 subnets. If we borrow 3 bits, we can have 8 subnets. /25 leads to networks of size 128 IP addresses. /26, you have 64 IP addresses. /27, 32 IP addresses. /28, 16 IP addresses. /29, 8 IP addresses. /30, 4 IP addresses. And you must deduct always 2, network address and broadcast address, to get the number of hosts, interfaces you can support with IP addresses. In this table, you see a class C network is divided into 2 pieces with /25, in 4 equal-sized pieces /26, in 8 equal-sized pieces /27, and so forth. And the smallest one with network address and broadcast address is /30. In this example, we see subnetting, but we also see so-called supernetting, because there's one network with more than 254 hosts, headquarter with 500 IP addresses required, and here we do supernetting. We move the ones to the left in the network mask. It's a /23 network now. You have 9 zeros in the host part. 2 to the power of 9 is 512, and 512 can cover these 500 required IP addresses. Then we have the second largest network of 200 hosts. This could be done with a Class C network. Then we have 50 hosts. This could be supported by a /26 network. 20 hosts, legal office, can be supported with /27 network. And then there are wide area network links, point to point, and we only have 2 interfaces, one router here and the second router there. We need 2 IP addresses, but we need a /30 network to get 4 IP addresses, including the network address and the broadcast address. In this example, there's a given address range, 172.16.00/22. It could have 1024 IP addresses in the network, could connect 1022 hosts if you would not subnet it. By subnetting, we get several subnets, the HQ subnet with /23, the sales office with /24. So these 2 already cover 3 Class C networks, and then we have smaller networks subnetting Class C. In the end, the first IP address for the first network is 72.16.00/23 for HQ. Then the next Class C network is 16.2.0/24. Then the next Class C network would be 72.16.3.0, but now we need a mask of 26. We can start at 0 for this subnet, and we can continue at 3.64/27 for legal office, and then we can continue with 3.96/30 for addresses, 100/30 for addresses, 104/30 for addresses. In IP version 6, the idea is to get an increased address space, 128 bits instead of 32 bits, only classless addresses, and the header is simplified now compared to IP version 4. Fragmentation is forbidden, and we have some scalability and flexibility by using additional headers here, but we also need some additional new protocols for IP version 6. Comparison of the 2 headers, 20 bytes in IP version 4, 40 bytes in IP version 6. So 2 times larger is the header, but you see less fields. And most important part of the header is the source address and destination address, which is 4 times larger than IP version 4. The time to live has been renamed into hop limit. The protocol field has been renamed in next header. It shows what's the next header following the destination address. And traffic class is type of service. Version remains version. And the flow label is a new label which identifies individual flows. Just a notion. If you have a maximum transfer unit of 1500 bytes, then the TCP maximum segment size is now reduced to 1440 bytes because of 40 bytes header in IP version 6. Now, looking into IP version 6 IP addresses, they have 128 bits, 16 bytes, and we can't use dotted decimal notation, but we use hexadecimal notation. 2 bytes hexadecimal, then colon, then the next hexadecimal values for 2 bytes, colon, and so forth. And one sequence of zeros may be shortened to colon, colon, and leading zeros may be shortened as well. So the IP address here is shortened to 2000 colon 0 colon 631 colon colon A567 colon E1. Traffic class is remaining. Flow label is really new. It simplifies flow filters. Next header can be used to signal TCP or UDP or some IP version 6 header. And we have some stateless address auto configuration. An IP version 6 address always have 64-bit prefix, which is the network part, and 64-bit host address. Little bit different concept to IP version 4. For example, our web server is host 2001.638.402.1300:7/64. And the network is ending at 1300. And we got prefix we can use in our lab with /56. Means there are 8 bits left to create subnets in our lab, and 2 to the power of 8 is 256. We can create 156 subnets, and each subnet would be /64. Our prefix is derived from the university prefix, which is /48, and this is derived from Deutsche Forschungsnetz, which is 32, and the IP addresses IP version 6 of DFN has been given by RIPE, which controls IP addresses in Europe. So we have some hierarchical routing in IP version 6. The stateless address auto configuration is really simple because it takes the MAC address of the interface card, and from the 6 bytes MAC address it creates an 8-byte host part of IP version 6 as a EUI64 address. And between the first half and the second half of the MAC address we have FFFE, 2 bytes. And in the first half, the 7th bit is flipped. And then there's the stateless address auto configuration process by the neighbor discovery protocol. We have some router solicitation, some router advertisement, some neighbor solicitation, and some neighbor advertisement. And then your device has a legal and valid IP version 6 address. The gateway function is shown in this picture because you can switch from technology to technology, here from Ethernet in the first router to FDDI, in the second router from FDDI to PPP, and in the third router from PPP to Ethernet again. But you also see fragmentation, which we should prevent. There's a maximum sized IP packet in the beginning, 1500 bytes. This can be transmitted in FDDI because the MTU of FDDI is large enough, but we have a problem on the PPP link. Here the IP packet must be cut into 2 pieces because PPP has additional overhead 8 bytes, and this deducts the MTU in 1492. Very often PPP is used as PPP over Ethernet at DSL dial-up links. Now 2 packets carry the content which was originally sent, and in router 3 these 2 packets are received, encapsulated in Ethernet again. They are not reassembled, but both packets are sent as they are, and only at the destination these 2 packets will be reassembled. Routing is a very simple process. Here are the symbols for routers or layer 3 switches, which can route as well. And any router knows the connected networks. The remote router here has network 10.1.2.0/24 and 10.1.1.0/24. And it must know the network between these 2 routers. 192.168.1.2/24 is the IP address of the router here. The network is 1.0. So this router knows 3 networks. The local router here, we don't know which other networks are connected, but we know the network to the remote router. But we do not know the IP addresses of the remote networks until we create a routing table, and in the routing table these 2 networks 110/24 and 120/24 can be reached using the same remote router to reach these networks. And if a packet shall be forwarded to the destination here, there's a lookup which IP destination address is used by the IP packet. Do I have a network which matches to that IP address? If yes, what's the next hop and what's the forwarding interface? Physical interface here, maybe gigabit Ethernet 0.1 or whatever. And then this packet can be routed. If there is no entry in the routing table, the router will drop the packet. So anything which is not known by the routing table cannot be routed. If there are too many networks which are not known, maybe you create a default route, and this is very often used to connect to the internet. Any network not known will be routed by the default route 0000/0, and the next hop is the default gateway. Again, the routing process, the routing tables must be implemented in routers. And in this example, from source 81.26.1.24 to destination 200.112.2, there is a packet sent over the network. And in each of these routers, there must be a check whether destination IP address is matching to networks in the routing table. For example, in the first router, we have a default route, forwarding over interface Ethernet 2. And the routing tables might be either created by configuration or by some dynamic routing protocols like Routing Information Protocol RIP, Open Shortest Path First OSPF, or Border Gateway Protocol BGP. Next topic on IP networks and routing is IP tunneling. It's important when you want to connect some remote site or some traveler or home office to main site of a company, and you use public infrastructure, but locally you have, for example, private IP addresses. Then you must encapsulate the internal IP addresses into something which can be transmitted over the public network. And the concept here is tunneling, and tunneling means you take an IP packet and encapsulate it in outside IP packet which can be routed. And at the receiver, you remove the outside IP packet header and get the internal IP packet and can work with that again. There are site-to-site VPNs and remote access VPNs. And by this technology, you can connect to the THCOL VPN. For securing the tunnel, IPsec is a protocol which is very often used in the tunnel mode. And this means we will use some encryption and also some authentication to secure the tunnel so that nobody can read the content. In this example, we have site-to-site VPN, 2 routers. And what you see here is the original IP packet, which is used inside the local area networks. And then at the security appliance and tunnel endpoint, you will encrypt this content. You will add some IPsec ESP header and ESP trailer. You will also add some ESP authentication data. And then you add an outside IP header to be used in the internet, and routers in the internet just read this outside IP header and forward to the destination address in this header, which is the security appliance on the other side. There you decrypt the content, you take the inside IP packet and forward it to the host. Finally, some words on quality of service. In IP networks, the internet doesn't support quality of service, it's just best effort service. In virtual private networks, you either have no quality of service if you run over the internet, or you have a dedicated VPN with some connections from public providers. And in these VPNs, you can get some quality of service, for example, to support voice over IP, very often implemented by DivServ technology and MPLS. And in next generation networks, they are designed to support quality of service for different services, and we will talk about that later on in this class. Some protocols with quality of service are listed here, and it's part of AMC class in winter semester, so you can use concepts like INTSERV or DivServ or MPLS. And on layer 2, it's 802.1q to have class of service in layer 2 networks. I skip ATM here.